All right. So Monday we started talking about greenhouse environments, and this is the week of greenhouse environment. And one of the students asked a question. This is a Chinese greenhouse, and then the purpose of Chinese greenhouse is absorbing radiation in this north wall, so that it can be the heat sink, and then it can be the source of the heat during the cold winter night. So to increase the radiation, how about putting mirror on that wall, which is a great question if you want to increase the light intensity, and then distribution, uniform distribution, if that's the priority. But that mirror is basically reduce the energy absorption over the wall. So it's usually not the case. Usually they want to select the material that can absorb the radiation easily. And then also there's one typical misconception here. Mirror works for direct radiation only. Okay? Diffuse radiation, basically the beams are everywhere, right? So the mirror doesn't quite reflect back to the direction you want to. It bounces back, but it goes up, goes to the sideway, everywhere. So may not be effective way to either concentrate or redirect to a certain way. Okay? Yes, Jessica.
What about in the case of the white cover on the floor?
It's the same way. So the direct light is, if you want to have a certain target area, then it works for direct light. But if you just want to reflect, no matter which direction, and then that's probably the case for the floor cover in the greenhouse. You just don't want to let the radiation absorb by the ground, but just reflect back to wherever, so that eventually it lands on the plants, right? So in that case, white cover works for both, direct and diffuse light. Okay. All right. Any other questions regarding direct and diffuse? The second question is photosynthesis efficiency. It's low efficiency, so I think it was like a 14%, the energy absorbed, photosynthetic active radiation energy absorbed, and then that was the ratio of the carbohydrate as a chemical energy fixed by photosynthesis, and that efficiency is only 14% or so, or 15%, and that's because the way photosynthesis is. Photosynthesis, the chlorophyll absorb the energy and transfer into the photosystem, and then every step it loses some energy either by heat or fluorescence, and then so that's why at the end it's very low efficiency. So because of nothing is perfect 100% efficiency. Anyway, okay, good. So let me get this. Close this. Second one up. Close that. All right, so this is the second lecture of the greenhouse environment. A lot of engineering stuff, and then again, this is the essence of what you may learn or you have already learned in the greenhouse systems and design course. There are 3 reading materials in your DTL. The 2 are very simple, short articles. The first one is extension article from Rutgers University talking about glazing and heat transfer. Because today focus is going to be heat transfer or energy balance, mass balance. Second one is the CO2 environment coming from the Plant Growth Chamber Handbook, which is online materials. So one of the chapter is the one I'm sharing today. And then the third one, which is quite advanced content. So unless you really want to learn in depth about greenhouse energy thermal properties, you don't need to read this. But if you are interested in this area particularly, and then if you are in the engineering program particularly, I would encourage to try that chapter coming from my one of the reference book. All right. Okay, so greenhouse energy source, obviously, solar radiation. And greenhouse is designed to capture the solar radiation in two ways for photosynthesis, we talked about Monday, and then also thermal, so that warming up, increasing temperature. In an arid environment like this, increasing temperature is appreciated only certain period of time. Even winter time, we need to reject the heat, otherwise it gets too high inside the greenhouse. So the greenhouse is more like a protection from maybe wind or dust, maybe capturing a little bit more humidity inside rather than the heat. But traditionally, greenhouse is to capture the heat so that you can grow, your plants for extended period of time. So this is a sort of the solar radiation budget at the glazing level, right? Incoming radiation, transmission, reflection, absorption. Okay? And then we talked about this, how little energy-wise we are eventually using for crop production. And then we could think of many ways to enhance the final percentage. By the way, I changed the loss by respiration. So the loss is 40%, and then so gain is 60%. So the parameter should be 0.6 instead of 0.4, which is the old version. So that's why the values, if you compare with previous lectures handout, the values are slightly different, but not much. It's basically less than 1% eventually fixed as harvestable product compared to the original energy coming from. Okay, so we did a lot of energy balance earlier, right? Energy balance over the leaves, net radiation, sensible heat, latent heat, the change in the system, change in the temperature of the leaf. And then we expanded idea to the canopy level, same way, And then now I want to talk about energy balance of the system, greenhouse. Right, so again, energy is coming in the greenhouse, and then midsummer radiation is about 1,000 watt per square meter. Okay, that is about 2,000 micromoles per square meter per second photon flux, photosynthetic photon flux included. So it's equivalent to that high level of ppf, photosynthetic photon flux. But midsummer is about 1,000. So the 1,000 watt energy, right? It's a radiation, but it actually absorbed. So basically, it's heat is coming in. And then we already learned that the use of energy for photosynthesis is very small, less than 1% or maybe 2%, So basically 99, 98, 99% are going to be heat in your greenhouse system. So if you can't understand the 1,000 watt level of energy, you can think about 1,000 watt heater, electric heater, running every single square meter of your greenhouse. It's a lot of energy, okay? It's a lot of energy. So therefore, particularly that heat is too much. And most of the summer, summertime, it is too much when you apply that in a closed structure. So you need to reject the heat by either ventilation or active cooling. All right? So that's what we are doing, either ventilation or evaporative cooling, reject the heat or remove the heat from the system. So let's look at a little bit further the balance of energy in the greenhouse. So when we talk about energy balance, we have to sort of think about the boundary. And then in this case, our boundary is the basically the outer layer of the greenhouse, okay? So we are not talking much about internal change. So we are looking at boundaries, so that heat transfer between inside and outside of the greenhouse. So the convection, conduction, like a sensible heat, right, going through the wall and then go out or coming into the greenhouse when greenhouse is cooler. So it's totally depending on the temperature, whether outside is warmer or inside is warmer. So that would, determine the direction of the heat transfer, right? And then the second component here is the net radiation, the same one, the short wave radiation, long wave radiation. Long wave radiation is coming from, the sky and surrounding objects, right? And then also upward long wave radiation coming from the plant surface, going out through the glazing. So that basically the sum of downward and upward short wave and long wave radiation is the net radiation. That's a big component during the daytime. And then when temperature is too much, then you often want to reject the heat by ventilation. So the ventilation heat transfer, removing heat from inside to outside, is also a big component in the greenhouse, right? If the outside is very cold, you are in the northern climate, and then you want to keep greenhouse warmer. In that case, the heat transfer through the ventilation may be very small. It's only what we call infiltration. It's very small through the cracks and through the gaps. So that's heat transfer. And then one more component. If you have ground surface, sort of uncovered, so the concrete or the soil surface, gravel, and then it's radiated by solar radiation. Typically, you have the energy stored in the ground. And then also ground, soil temperature is stable, so that sometimes it's warmer than air temperature, sometimes cooler than air temperature. So there is a flux, meaning the heat exchange, depending on which side is warmer, which side is cooler, going on right here. So there are basically 4 main components in the energy balance equation of the greenhouse. And then last one is the internal change. So when you think about steady state conditions, temperature is not changing, all the components are stable. In that case, QA, this term is 0. But otherwise, you have to think about temperature change, which is the additional component in the energy balance. All right. So plants are doing evapotranspiration, okay, in a greenhouse. And then this slide is explaining evapotranspiration as a cooling mechanism, not only for the plant itself, which we learn in the energy balance of the leaf, energy balance of the canopy, but transpiration in the greenhouse of the plants is actually cooling mechanism of the system also. Why? Because so the plants exchange energy, so basically receive the net radiation, and then convert that into latent heat and sensible heat. Remember the energy balance of the leaf. And then latent heat component and then sensible heat component also eventually go out to the greenhouse through ventilation. All right? So that process is a cooling mechanism. Right? So if you enter the empty greenhouse under the same radiation level, you usually have much warmer temperature. But as soon as you put the plants in and plants start, absorbing energy and then converting that solar radiation and other energy, net radiation, into the latent heat, then that latent heat is going to go out the ventilation, through the ventilation. And as soon as it starts doing that, then you have much lower temperature inside. So this is the same mechanism as the evaporative cooling. Evaporative cooling is, you evaporate water from wet surface, or maybe the particles of water sprayed in the system. And then latent heat, right? So the latent heat is the change of phase, liquid to vapor, and then take up the surrounding temperature, energy, and then add as a moisture in the air. So that is a latent heat. So that part is, the latent heat is going to go out, injected to the outside of the greenhouse. So if you look at the energy exchange by ventilation, you can actually add this equation: ventilated heat equals sensible heat exchange by ventilation and latent heat exchange by ventilation. Okay, and in plant production system, latent heat in the plant production system is much higher than outside. So usually, latent heat goes from inside to the outside. Sensible heat inside the greenhouse could be higher, could be lower, depending on the season, particularly like in our kind of climate. And then in that case, sensible heat may be coming out or coming in from the greenhouse, depending on the temperature, which one is higher in terms of temperature, inside or outside, okay? All right, so we are actually a unique situation though. So the latent heat may be going out, but sensible heat may be coming in. So if you're engineers, probably easy to get that concept, but we are definitely very interesting situation. All right, let's talk a little bit about natural ventilation before going further in the greenhouse energy balance. So natural ventilation of greenhouse, again, is very important mechanism to remove the heat, and particularly well utilized in mild climate. Arid climate, we kind of want to limit the ventilation as much as possible because the dry heat is out there. So you don't want to put too much dry heat coming into the nice, microclimate we have by plants. So there is a pros and cons of the natural ventilation, and definitely we need to develop some technology to manipulate that ventilation rate, particularly it is natural ventilation. All right, there are two types of ventilations. One is natural ventilation. The other one is forced ventilation or mechanical ventilation. And then you can easily imagine in our teaching greenhouse, it's a mechanically ventilated greenhouse, big fans, pushing air out from the fans. And natural ventilation basically driven by the density of the air. Warm air has less density so that it floats, goes up. Cold air or lower temperature air is high density, therefore sitting in. And then if you have an opening in the side and opening on the roof, that distance between the low vent and high vent is the driving force, because that would create what we call chimney effect. So that would enhance. And then also not only that, ventilation rate is affected by outside environment, how much wind is going outside, and which direction relative to the the vents. So it's a whole set of knowledge and wisdom, research, confusion out there. So if you're interested, it's a lot of information out. I'm not going to go through too much detail in here. But anyway, those are the factors. Of course, the shape of the greenhouse, size and orientation of the vents, those are the factors as well. And why ventilation rate is important, because you see in several charts I have, or the drawings I have regarding energy and mass balance, every single one has ventilation as a key component to change the status. So it would affect air temperature, it would affect CO2 concentration, it would affect the water vapor concentration or humidity BPD. Okay, so that's why ventilation, understanding ventilation is very important. All right, greenhouse cooling systems. This is the most widely used greenhouse cooling system, pattern fan cooling. exactly the one we have in all these greenhouses. So wet pad in one side, mechanical fan the other side, putting air through the wet pad. Therefore, the latent heat, remove the heat from the air, and then create the cold and moist air there. And then that latent heat is going to be taken away by mechanical ventilation. All right, yes, Courtney.
What is that top picture showing?
Oh, top picture. This is what we call cooling corridor, cooling walkway of the commercial greenhouse. So the both sides are wet pad. And then the air intake is at top of the roof. So it's I don't know, it's like, yeah, it's like 2/3 of this classroom width. And then it's just like a one bay of greenhouse. And the other side, so left-hand side is one compartment, right-hand side is another compartment of the greenhouse. And then so the other side are the mechanical fans. And then also the other side, this way, mechanical fans. So that's shown in here. Okay, so it's a one design of commercial greenhouse.
Is there any research regarding the decrease in temperature when you enclose pad system? When you put the pads in a separate structure, so to speak, and they're not outside in the direct air?
Oh. Well, but the intake is from outside, though. Yeah, so this one is just the roof vents, and then air is coming through the vent. So it's the same air as outside. And then I think the cooling capacity is based on, yeah, so the cooling so how much, delta T or temperature deficit you get through the evaporative cooling is pretty much determined by the wet bulb temperature. So how much moisture that the intake air is containing. So whether it is a little bit warmed up in this corridor or the walkway or not doesn't really affect, because it's a moisture content. So if you have fogging in here, it would definitely affect the cooling efficiency. But as long as there's no moisture change through that process, the cooling efficiency is the same. All right. Okay. Yeah, so it's very much used in southwestern United States. It works really well. And however, there is a temperature gradients, right? Pad side and fan side. We found that, I think, in our measurement when we did that. All right. Another system potentially used for cooling is evaporative cooling system, which is okay system, but it's challenging to control. Pattern fan is more stable in terms of temperature. Fog system, high pressure fog system, tends to create a big up and down temperature, oscillation, big delta T. And then also, when the nozzle location is too close to the canopy, like a tall crop grown, and then the nozzle location is only, maybe less than 1 meter away, and then in that case, plants tend to get wet, okay? And then you don't want to wet the plants, because as soon as you wet the plants, plant surface temperature goes down to the wet bulb temperature, right? The wet bulb temperature. So that is usually a lot lower than your optimum temperature. So the photosynthesis goes down. And on top of that, disease management is going to be challenging. You don't want to create wet surface. All right, so for many reasons, this is not so well utilized. It is utilized for humidification. Required amount of water for humidification is a lot less than cooling. So that, injection of water may not wet the plants. That's why it can be used for humidification, but not so much for cooling. Caitlin, you have a question?
How significant would rust or calcium buildup be on the stuff inside the greenhouse?
Oh, it is significant. Oh, yeah. So usually you have to have a good filter system before, injecting yeah, so you don't usually do that without filtering. We do that in one of those greenhouses, but it's just because we don't have that capacity. The question was about the calcium scaling within the greenhouse. All right, okay, so anyway, so those are some of the pros and cons. Nice system if it works, but it is challenging. All right, so the nighttime energy balance of the greenhouse, most of the cases, right, you want to maintain warmer temperature than outside, okay? In here, because we are in arid area, sometimes you want to still cool the greenhouse, which is challenging because there's not much radiation coming in. Therefore, there's no, conversion of energy to latent heat. So, but anyway, understanding energy balance is very important to, minimize the resource use, particularly, and then also, microclimate, potential microclimate in the greenhouse, therefore your plant grows. So the nighttime net radiation is usually upward, not downward, right? Because the long wave radiation loss from the surface inside the greenhouse is going through the glazing, right? Glazing is not always opaque to the long wave radiation, therefore you lose the radiative heat. And then probably lot of transmission from the inside greenhouse to the outside. That's a convection conduction and ground heat transfer, and ventilation is probably minimum. You probably want to keep the greenhouse closed when you want to maintain the temperature inside. Okay, and then if that is not enough, then usually you have heater. So we have cold nights in, arid land, and then northern areas always it's cold. In that case, you have to have heating, and then add energy. So you lose energy, and then you compensate the lost heat by heating. Okay, so that's the greenhouse system during the night. All right. A little bit more about long wave radiation. It's a not easy concept, but I hope you still understand the long wave radiation coming from the surface having temperature greater than 0 Kelvin, right? So any objects having that, whatever the temperature, have that amount of energy emitted by long wave radiation, which you can't see. And then emissivity is the sort of optical parameter determining how much long wave radiation potentially coming from that surface. Okay, and then so the plant surface, ground surface, any surfaces you have in the greenhouse emitting long wave radiation constantly, right? But because during the nighttime, that's going to be the main component of the radiative energy loss. So that's why we need to understand a little bit better. So portion of the long wave radiation going through the glazing, okay, and then that amount, how much going through or how much going to absorbed or reflected, is depending on that material, okay, glazing type effect or the curtain. Sometimes thermal curtain is providing protection over the long wave radiation, and that's also important component. And then also the surface, the glass surface or a plastic surface has temperature different from sky radiation. And then according to the emissivity of that material, there is both ways long wave radiation emitted. Okay, so that's a sort of balance. And then, sky radiation, right? Okay, so let's look at the three sort of representative materials I want to talk about. So as I said, glass is relatively opaque to long wave radiation. So this is a sort of upward radiation, so that the plants and ground and everything is emitting long wave radiation coming up. And then the blue line here is the glazing, and this is in case of glass having a high infrared long wave absorption. In that case, it's absorbed and then less transmission going on. Okay, and it is absorbed and emissivity is relatively high, so there is a re-emission going on. But as a whole, the absorbed or retained energy is relatively higher than the other example, which is a polyethylene film. And polyethylene film is quite high in terms of transmission. So you lose a lot of long-wave radiation when greenhouse is covered with polyethylene film. Hoop house, particularly the case, single-layer hoop house, you lose a lot of energy by long-wave transmission. And then, so very small amount is the gain. So therefore, energy-wise, it's not efficient, right? So one strategy in that case is to protect the long wave radiation transmission by using aluminum cloth. So that there are multiple materials available in greenhouse, and an internal shade cloth having aluminum materials included, and that is having very high refraction of long wave. So long wave radiation now reflected huge. It doesn't transmit either. And therefore, you save a lot of energy, retain energy inside. So that's one very effective way to reduce the heating cost in the cold nights in the greenhouse. Okay. Some of the shade cloths can be used during the day as a literally shade, creating shade to block the shortwave radiation, bounce back to the atmosphere, basically. So this is an internal curtain used in the daytime as a shade cloth, and during the nighttime reflect back and then retain the energy when temperature is low, okay? When temperature is low. Okay, another material may be a different type of plastic materials, and then it's also shade cloth. And then also, having that layer would create warmer temperature surface compared to glazing surface. When outside temperature is very, very cold, glazing surface is also cold. In that case, the long wave radiation emitted from that surface is, is very low or a small amount compared to the surface like internal curtain, because the internal temperature is usually much warmer than outside. Therefore, this surface temperature is few degrees higher or more degrees higher than the glazing surface. In that case, you have more downward long wave radiation coming to your plants, and that means plant temperature potentially warmer. And then I don't know if you remember, we had that issue in the polyethylene covered greenhouse. Our tomatoes were not ripening fast enough, and I realized that it's probably the cold plant temperature during the cold night, and then we started putting the shade cloth to maintain the temperature, and that helped a lot, the ripening speed. All right, another typical strategy, which probably you see in the first reading, is the insulating greenhouse. Caitlin, you have a question?
Yeah, sorry. On your previous two slides, other than the different type of shade cloth, I'm struggling to see the difference, I guess.
Difference in terms of?
I guess their effects, because it looks like long wave radiation is still being transmitted from the plants and then reflected off the shade curtain back down. And I just wasn't sure what.
Yeah, so this, I guess the difference is the strategy. So this is a reflection based, okay? And then the other one is the emissivity based, emissivity and temperature, okay? So the higher temperature and higher emissivity versus the one before is the emissivity itself is very low, but reflects a lot, okay? All right, so different strategy. Which one is more effective? I guess I have to say depends. Yeah, but I think deflection is pretty straightforward, and I think it works really well. Okay. Yeah, so the insulation. So the double wall is a typical way to increase the insulation of the greenhouse, and then that would basically reduce the transmission through the glazing. All right. Sorry, I need to cough. Okay. All right. Yeah. So that's typical, and then also creating internal layer a little bit higher temperature would help in terms of long wave radiation. So there are two ways. So that's why I have little bigger arrow looking at internally. All right. So any questions so far? Okay. Okay, so the next part of this lecture is a mass balance. Then I'm going to talk about CO2 first, and then going into water. Water is important, but I want to talk CO2 first. All right. Just to remind you, the plants respond to CO2, right? This is a CO2 response curve, and then they want to have probably 2 or 3 times greater CO2 concentration to maximize their photosynthesis. That's why we have opportunity to inject the CO2 in the closure, like greenhouse, to maximize the photosynthesis. Plants can utilize the CO2 until it reaches the CO2 compensation point. Once the CO2 concentration reaches the CO2 compensation point, the photosynthetic or the net photosynthetic rate becomes 0 because the respiration and gross photosynthesis balances. All right, so let me do a little exercise and then switch to Elmo. All right. Okay, so I have a plant, and then I have a very, complete airtight box. So I put the plant inside a airtight box, and then this is the dark, complete darkness, no lights. And then I have a sensor that measure the CO2 concentration inside the chamber. If I draw graph like that, this is the time, and this is a CO2 concentration. I have my plants in here, live plants, okay? So the starting point 0, and so ambient CO2, what is ambient CO2? 400 parts per million, micromole per mole. So that's the starting point, CO2 parts per million or micromoles per mole. So in the darkness, how the CO2 concentration change, how does it change over time? Going down? It's darkness though. It's dark, dark, dark. Wouldn't change. So that when something is producing CO2, then it goes up, right? If something is consuming CO2, it goes down. If nothing is happening, no production, no consumption, then it goes straight. Okay, so in darkness, plants produce CO2 or absorb CO2? Produce. Respiration, right? Respiration going on. Okay, and then the rate is constant rate. And if something is, producing CO2 at constant rate, then you would see linear increase. Okay, make sense? So the speed is not changing. So the linear increase like this, right? Okay, Right. This exercise is very important to get you the concept of mass balance and how things changes in a system. So that's linear, right? So the question number 2, okay, so after this, okay, I know plants need light, so I'm going to turn on light, all right? And the question is what happened in the CO2 concentration. So let's draw again. So that's time, hour or second or whatever, maybe minutes. And that's CO2 concentration. So that's the time 0. And I started from 400, right? And it linearly increased to a certain level. So this time is the darkness up to here. Okay? All right, so I turn the lights on, right? Okay, lights on. And what do you think in terms of CO2 concentration change over time? Decrease. Okay, and then what happened? Going down, and then until you get 400. Okay, so until you get 400. And then what happened? Continue going down. Why? It's sealed box, and the 400 level you can still do photosynthesis, right? Okay, so just a reference curve. So this is a CO2 response curve of the plants, right? So this is the PN, net photosynthetic rate, and this is the CO2 compensation point, which is lower than 400, right? That's what the concentration-wise, 50 to 100, depending on the species. Oh, sorry. There you go, right? Okay. Yeah, so that's better. Okay, so that's the reference, right? So let's discuss 400, right? And then continue, and then would that reach the bottom, 0? Because it's sealed. No, where is the stabilization? Bingo. At the compensation point, it's stabilized. Because it's 0, right? No production, virtually, no consumption. So therefore, stabilize that level and then just maintain that level, right? So that compensation point. So that the curve may be like this. Because it, the slow down when CO2 is getting lower and lower, and then stabilize. This is probably 50 to 100, depending on the, species compensation point. Good. All right. One more. Okay, so I notice. Oh, no way. I can't, illuminate the box with plants without, doing anything. Otherwise, I'm going to, because under this condition, no net photosynthetic rate, right? So that means no growth, no gain, right? So it's nothing. So I need to do something. So what do I need to do? I need to do ventilation. So now, okay, again, time. That's CO2 concentration. And let's see. So started going down. So this is 50, let's say 50 parts per million in this case. And outside level is, so this is outside level. This is 400 level. Okay? All right, so I open up the vents. I made a hole or I made a little window, and I did that in here, this timing. And how does it change, the CO2? Caitlin.
It'll drastically increase until it reaches 400, in which case drastically increase through the diffusion from the outside air since it's at 400 going to 50?
Huh? It's drastically increased until it reach 400, and then
And then it should stabilize.
it should stabilize.
And that's assuming that you don't close the vents and that you're allowing it to.
Well, I'm keeping the vents open, so that's my question. Okay, so it reached 400. Okay, do you all agree? It reached 400.
Then it's stabilized.
It might oscillate, but it shouldn't because.
Oscillate. What is causing that oscillation?
Well, I actually take it back. I don't think it should because you're still going to have diffusion from outside, like here, even though.
Yeah.
Even if you're
Yeah,
close to-
yeah. So okay. So think about a lot of ventilation going on and small ventilation going on. If it is a lot of ventilation going on, and okay, would that change the stabilization level? When
Ventilation?
yeah, amount of ventilation.
It would, because if you had very little ventilation, I think over time you'd have a flat line, but in like the local, very small area right around the plant, it would probably go up and down. But the total would remain flat if you had at least large ventilation. It would remain stable.
Total. So okay, so yeah. So this is well mixed.
It is well mixed?
Yeah, it is well mixed.
Said it would be stable.
No matter how much ventilation is in. So it's only teeny tiny airstream going in. Before,
I think there would be a change.
okay?
I think it would.
Would stay below 400 if the ventilation wasn't enough.
Yeah. But
It would level off at a little bit below 400.
Yeah,
Because you'd still be getting some of the mixing.
yeah,
If you're not getting enough ventilation,
yeah,
then it's not going to.
yeah. So, okay, so here, so the stabilization depending on the ventilation rate. Okay. If it has enough ventilation, then the CO2 inside the box is getting close to the outside. So you can think of in a heat. You know, you have a heat trapped in a system, right? If there is a massive ventilation going on, then temperature inside is equal to outside. If it is limited ventilation going on, then temperature is going to be a little bit away from outside. Same thing. As long as plants are consuming, so there is a consumption going on, right? So the CO2 is taken up. And then ventilation is supplying the CO2 according to the concentration difference. And then when ventilation is small, then that would reduce still the CO2 concentration inside. Okay? Haiti.
If ventilation was really small, though, wouldn't, like Caitlin said, wouldn't it oscillate? Because, so if ventilation was really low, then, so it would go up to 400, and then the plant would start photosynthesizing and releasing,
Yeah, initially. So that if you are changing things very rapidly, boom, and then you have this kind of oscillation, but it's stabilized anyway. Because plants' photosynthesis basically balance with the supply of CO2 coming by ventilation. And then photosynthetic rate is determined by the CO2 concentration. So that steady state is achieved eventually. So initially it may, because it's a sort of disturbance. So the bouncing and then just go into the stabilization. Okay?
is the plant's response to CO2 immediate, or is there some sort of like a feedback wait time where the CO2 is increased, photosynthesis starts immediately as soon as the CO2 is increased in the environment, or is there like a lag?
Yeah, so remember the CO2 absorption is diffusion. The question is how fast plants respond in terms of CO2 change. It's a diffusion, and then the ventilation is also diffusion in a sense. I mean, the CO2 supply by ventilation is, the massive amount of air, but still the temperature difference, I mean, not the temperature, CO2 difference in and out. So it's the same. I think the mechanics is the same. So it's not, I don't think you start seeing that oscillation you're thinking because of the difference in terms of reaction speed, between plants and ventilation. But that's my experience, because I dealt with many closed system CO2 measurement, usually very stabilized at the end. All right, okay. So I think what you understand is so far so good. And then I want you to apply that understanding in this chart, which is the CO2 concentration in that greenhouse compared to the outside. So it's more dynamically changing environment. So it's not stabilized situation, right? Because radiation is changing, photosynthesis is changing, wind is changing, everything is changing. So in that case, you don't see the straight line. But because you have now good understanding, I think you can understand what's going on. So this is the time of the day, during the day, 6 a.m. to 6 p.m. And then greenhouse CO2 concentration is here, and outside CO2 concentration is here. It's relatively urban area, therefore lots of activities. That's why CO2 outside is not stable. And then this is all data, therefore CO2 concentration was not 400. It was more like 350, 330. All right, so the beginning of the day, CO2 concentration was relatively high. And then higher than greenhouse, outside, sorry. Inside greenhouse, concentration is higher than outside. Why? Because respiration, right? Greenhouse is closed, and then plants are respiring. Therefore, CO2 concentration inside is higher than outside. And then as soon as sun comes out, CO2 goes go down. Very quickly, very quickly, very quickly, and then it reaches, in this case, 200-ish, right? Definitely lowering photosynthesis, right? Definitely lowering. This is within 2 hours of time. So that is affecting photosynthesis. And then this greenhouse vents open, not for CO2 most likely. It's usually for maintaining temperature, okay? And temperature goes up, therefore vents open. And then that helped the CO2 coming in to the greenhouse, and then increased very fast. And then it stabilized around the 340 or so, and then following the change of outside CO2 concentration. So that delta CO2, the difference of CO2 is because of the photosynthesis. If you have plants in a system and plants are photosynthesizing, unless you have a massive amount of air going through the system, you always have small, at least, difference, and always lower CO2 concentration inside than outside, as long as plants are absorbing CO2, okay? If you want to, anyway, so that's going on here. And then side vents open, so that ventilation rate increased. So now you see the delta CO2 reduced, okay? If the ventilation is getting higher and higher, you have the CO2 concentration in the greenhouse, closer and closer to the outside, okay? All right. And then, oops, I keep doing that, sorry. And then maybe temperature gets cooler and vents closed, and then as soon as vents close, the CO2 start climbing up again. Maybe the light intensity is low, therefore, lower than light compensation point, okay, light compensation point. So more CO2 production, therefore the CO2 increase and higher than greenhouse, and so that's That's the one, 1 day snapshot of CO2. And then remember, this CO2 concentration is affecting the plant growth, right? Affecting the plant growth. So you want to obviously inject CO2 during this time, okay, to avoid that negative influence of low CO2. Or you might want to try to inject the CO2 during vents are open, at least to the level similar to the outside, right? Similar to the outside, so that you can enhance the photosynthetic rate. All right. So when plants are exposed to low CO2 concentration, what it does is basically slowing down the growth, slowing down and lower yield. So that's the typical. And the challenge, as I mentioned in earlier lecture, you can't sense the CO2. Humans cannot smell the CO2. So unless you have a sensor built in, you really cannot see the problem. So you need to be careful whenever you grow plants, and then prolonged time of the greenhouse is closed without having CO2 enrichment system. And then I have a series of slides in here talking about opposite effect, high CO2 concentration. I probably should have included those slides in a CO2 lecture, but just to recap some of them. And then also some of them I probably haven't talked about. But those are coming from the second reading material. Mary P., who is now with USDA, did a lot of study of high CO2 and tomato crop. But anyway, you can increase photosynthetic rate and adjust the sink-source relationship. And then another thing is, remember the high CO2 increase the stomatal resistance. So the stomata tends to close a little bit under high CO2, which is very well known plant response. And then in that case, because you have high CO2, photosynthesis is enhanced because it's diffusion, right? Internal CO2 outside is much higher, therefore photosynthesis is enhanced. But because the reduced stomatal resistance, transpiration is also reduced. So now you are doing more photosynthesis with less water loss. And that's what we often say, water use efficiency is enhanced by CO2 enrichment because of the stomatal change, the resistance change. All right, TJ.
Has anyone done a cost analysis on that?
Cost analysis,
Water
yeah,
increase in CO2.
CO2 enrichment is effective way to increase the yield, and suppressing water may not be so much reducing cost, isn't it?
Yeah, I'm just wondering if, say, $20, they get to spend $40
Yeah, so I would say yeah, so CO2 enrichment is a good thing. So you save water a little bit and enhance the yield. However, there's a case CO2 enrichment doesn't work in terms of cost. You can still enhance the growth, but too much cost for the CO2. So that's the kind of cost analysis you need depending on the source of CO2. All right, and so those are pretty much typical response. So I'm going to skip those altogether. So let's talk about CO2 concentration used in the greenhouse. So when vents are closed, definitely you want to inject high CO2. And target CO2 is 1,000 to 1,500. That's the level you can achieve easily without influencing any other humans, okay, working in that high CO2. It's not too high for human. When vents are open, you lose a lot of CO2. If you do this 1,000, 1,500 micromole CO2 injection. So you usually reduce, growers usually reduce to the level, but still higher than without CO2 enrichment. Okay, remember when plants are growing and ventilation going, depending on the ventilation, you can't really achieve the ambient CO2, but you can inject the CO2 and achieve that 400 level by CO2 enrichment. And then the source of CO2, liquid CO2, which is usually more expensive than combustion system, and therefore combustion system is more common in greenhouse system. However, you have to use high efficient conversion system, otherwise you end up with all the toxic contaminants in the system, depending on the source of the gas too. All right, so this is a liquid CO2 cylinders, massive ones used for CO2 enrichment in the plant production system, including greenhouse. This is a combustion system to generate CO2. And then the right-hand side is actually the boiler to create hot water for heating. So during the night, this hot water is introduced in a greenhouse for warming the plants through the radiative heating. Okay, and then during that process, CO2 is produced also, so that CO2 is injected to greenhouse for enhancing photosynthesis. And then this is a small version of combustion system, which is burning natural gas to inject CO2, which is the one in the teaching greenhouse. Okay. And then CO2 analyzer to measure the CO2. All right, so let's talk about CO2 balance in this slide. So if you look at the components we talked about in a little exercise, so those are the two. So the plants either respiring or photosynthesizing, producing CO2 or absorbing CO2. So that would affect the balance of the CO2. And then this is a gas exchange, so the amount of CO2 released by or coming in by the ventilation. So that CO2 outside is higher than CO2 concentration inside. Obviously, CO2 is coming into the system through the ventilation. If it is inside, it's higher than outside, CO2 is going out, right? It's very straightforward. And then the factors here are how much ventilation going on. So the N is the number of air exchanges. Number of air exchanges meaning how many times of that volume equivalent air, volume of the greenhouse equivalent air exchanged per hour. So if it is one time air exchanges, that means one time of the volume of the greenhouse. That amount of air is exchanged per hour. And then so multiplying two values, number of air exchanges and volume of the greenhouse, then you can get ventilation rate, volume per hour ventilation rate. Okay? And so if the ventilation rate is higher, then the supply rate when CO2 outside is higher than inside, supply rate is higher. And therefore, the stabilizing CO2 concentration or the final CO2 concentration would going to go closer and closer to that outside level. So that's the balance of two components. When CO2 concentration is high in the greenhouse, it loses a lot. When ventilation rate, the N number is high. So that's why you can't really increase the CO2 when ventilation is high. Another big composition, when you are growing soil-based system, in Mexico there are lots of greenhouses still using soil, even though the structure is medium tech or high tech. Asian countries too. And then soil is a great source for CO2. If plants are growing in the soil, microbial activities, so you have another source of CO2 in that greenhouse. So you may not need this injection of CO2. Okay? All right.
There, but only if it's required, right? You only have to use it if it's required. Here, you have soil base.
Only if it is required.
I
Like
mean,
if the CO2 levels are low.
yeah. Just like in case of
Huh? I don't know what you are talking. CO.
It's always good to have the CO2 producer there.
Oh, the injector? Yeah.
Just
Yes.
in case.
Yes. But the amount of CO2 you would need would be affected by what kind of system you are using. So yeah, so it wouldn't eliminate. So I think you are in the context of soil-based system.
Yes.
Yeah. So the soil-based system is good to maintain the CO2 a little bit higher than the concrete-based system or soilless system, right? So if the greenhouse is closed entirely, I'm not sure. I probably don't think the soil, the generation of CO2 from the soil would supply enough CO2 for the plants. And this one is actually showing the two different systems, soil-based and soilless, over time. And you can see that soil culture maintain the CO2 concentration relatively higher during the time radiation is low. So this is a nighttime, right? So the nighttime, of course, high CO2. That doesn't do anything, right? Plants do not do photosynthesis. So the high CO2 at night doesn't really do anything. But as soon as sun comes out, still, soil-based system maintains CO2 a little bit higher than the soilless production system because it doesn't have the source of CO2. So that few hours of difference might create some difference in terms of photosynthesis during that time. I don't know why the soilless was, maybe this is CO2 injected, or I don't know, maintained at certain level. So in this particular system, particular data set, it shows a little bit lower CO2 concentration in soil-based system during the rest of the daytime, which I don't have a good explanation for that. All right, water balance. I think I can finish. Yep. This is a components of water balance. Again, ventilation is a big component to think about the amount of water lost from the greenhouse to the outside. And then other components are injection or irrigation water, drainage water, transpiration, and cooling water, and condensation over the wall. So those are the components in terms of water balance in a greenhouse. So so that's the balance of the equation. And this is an actual measurement. I think it's in England. It's in England. They measured. This is I think in the winter time. So there's no cooling water, irrigation water, and pretty much high percentage is lost as transpiration, and very small loss in the ventilation, and then a lot of condensation going on, and that could be recovered as irrigation water. And then you see in the next slide, the value is very different. This is a summertime. This is a winter time. The big difference is the water loss through the ventilation, and then also irrigation. So that's one example of the two different seasons water balance. And then I think if one wants to, either save the water in a production system, we need to look at this kind of balance, how much water is used for irrigation, how much water is used for cooling system, and that would help to develop a strategy to optimize the environment. So there are a few greenhouse videos I want to show. You are encouraged to go to the website. The first one is basically the list of videos introducing Wilcox greenhouse in Wilcox. It's very nicely done, 10 years old almost, but it's still very informative. And then you have one homework question out of one of the videos coming out from this series. And so you will see that video, and then others are also available in this link. Two others. The second is a semi-closed greenhouse in California, commercial greenhouse. And that's the design. I think it's probably, right now, we consider the best working in arid area. Enrique asked the question Monday, what design is good? And that's, I think, in my understanding, is the one we think works really well in this region. So that's, it's called semi-closed greenhouse. The strategy is limit the ventilation, okay? But we want to still cool, okay? Right now, pattern fan greenhouse, we are venting massively, so we lose a lot of water to the atmosphere. We have to use a lot of water and then lose that water. And then we can't inject the CO2 because we have a lot of ventilation going on. So this concept, semi-closed greenhouse, is limit the greenhouse ventilation a little bit so that increase the CO2 higher, and then internal circulation to repeatedly cool rather than one stream going out. And then also, because natural ventilation is reduced, there are less number of vents over the roof, therefore structure is reduced, and therefore the shade components reduced, more lights coming in. So that's why many commercial greenhouses now testing this greenhouse design. California, Texas, Arizona, the new greenhouses are 100% actually this greenhouse design, because those early adapters show that high yield, like 100 kilos per square meter tomato yield was achieved using this one, which is amazing yield. So now it's getting to be a standard in my observation. So there is an internal air circulation and air distribution plenum. If I have a chance, I would spend a little bit more to describe how it works. But second video is showing basically this semi-closed greenhouse. It's slightly different design, still using pattern fan, but different air distribution and air circulation system. Okay, I think that's the last. Yeah, all right, good. All right.